Hey again everybody, and well done on completing lesson 2.2 of the Discover the Aurora course, in which we learned about the magnetic field of the Sun. And again, as before, we're just going to quickly sum up the key points in the lessons so that we're well equipped to move on with the course. First of all, we learn that the Sun rotates on its axis. And before that, we also learn that the Sun consists of charged particles, plasma. Now, if you move charged particles around, you generate a magnetic field. The Sun is moving charged particles around as it rotates on its axis, and so we can say that the Sun has its own magnetic field, which, if you simplify it, looks quite similar to a classic dipole magnet. In the previous lesson, in lesson 2.1, we learned about the solar corona. The Sun's magnetic field traps the plasma as it leaves the Sun, and the plasma interacts with the magnetic field. The Sun, you could say, paints its own magnetic field in the corona, and in this beautiful eclipse image you can very clearly see a dipole magnet. You can see a north pole and you can see a south pole. It's not quite as uniform as a nice straightforward dipole magnet, but the magnetic field there is very, very obvious. The Sun's magnetic field gets tangled and stretched. This is called the omega effect. And this is because the Sun is rotating more quickly at the equator than it is at the poles by a difference of about 10 days. And so the plasma at the equator is moving more quickly than the plasma at the poles. As the plasma moves, as the Sun rotates, it carries the magnetic field with it. And this effect winds the Sun's magnetic field up. And you can see that illustrated in the diagram. As it transitions, it gets more and more tangled up. And this difference in rotation speed exists right down into the Sun. Think back to the previous lesson where we talked about the different structure of the Sun. And we had a quick look at that tachocline region, the transition region between the radiative zone and the convective zone. Conditions in the radiative zone are very, very different to conditions in the convective zone. And so where those two zones meet, there's a transition region called the tachocline. Now, in this region, the different conditions existing in the Sun could be said to shear against each other, the different rotation speed and the different composition. It's thought that the tachocline is responsible for generating and sustaining the magnetic field of the Sun. This region causes a lot of different magnetic instabilities which rise up through the convective zone. Imagine a giant horseshoe magnet rising up from the tachocline up through the convective zone and up to the photosphere, as we can see just here. And we can see those tangled magnetic knots as the plasma loops around on itself in the photosphere. And in a later lesson we'll see how this generates the solar wind, these magnetic instabilities generated by the tachocline, which sustains the Sun's magnetic field, generating the solar wind, which eventually moves towards Earth and can trigger the aurora. So there's a very quick recap on how the Sun generates its own magnetic field, with special focus on that interface region, that tachocline region, where the conditions of the radiative zone and the conditions of the convective zone meet and shear against one another as the Sun rotates. I'll see you later on for lesson 2.3.